reinforcement learning lecture. Today we're going to...
Are we already live?
We should be live.
Okay, introduce, then Doina start.
Go for it.
Hello, everybody. We're live from the MPI for Intelligent Systems in Tübingen, Germany, and welcome to the second session of reinforcement learning. And without further ado, let's welcome Professor Doina Precup.
Hi, everyone. Today we're going to have a pretty busy agenda. We're going to talk about control algorithms. I'll try to talk about both value-based as well as policy-based control. So Q-learning on one side, for example, and policy gradients on the other side. We will talk about exploration because it's a very important problem for learning how to control an environment, and also about knowledge representation in reinforcement learning agents, which is a topic that I'm very interested in my own research. So I thought I would share a little bit of that with you as well. So this is just a reminder from yesterday. The setup is we have an agent embedded in an environment. At every time step, it perceives the state ST of that environment. That's whatever observations are relevant for its decision-making process. It takes actions denoted AT. And one time step later, we're going to observe a reward, which is the number RT plus 1, and the environment will transition to some next state ST plus 1. And the goal of the agent is to learn from this interaction how to control the environment. So how to choose actions in the best way possible, the way that maximizes a notion of cumulative reward. And we discussed in the previous lecture what some of these notions might be. So how do we define that? So today we're going to focus on the problem of control. And if we make certain assumptions about the environment, for example, we assume that it is a Markov decision process and it is finite, then we know from the seminal work of Bellman that we can impose a partial ordering over policies that an agent might have. And in this ordering, we're going to say that a policy pi is better than some other policy pi prime if it is better at all states. And of course, V pi is this quantity that measures the expected cumulative reward of the agent or the expected return of the agent. And we discussed in the previous lecture a lot of different ways for estimating V pi. Now, what we would like to do today is actually to move to agents that are optimal or close to optimal. And so for this, there's another result that we need to be aware of, which is that if the environment is finite, there will be an optimal value function, which is denoted here V star. So V star of S means the best expected return that we can get from a particular state S. And this value function can be obtained by maximizing V pi over all policies pi. Now, obviously, this looks like a very daunting optimization problem. So a lot of the stuff that we're going to do today is talk about various approximate methods that we can use to solve this problem. Another important quantity that we're going to talk about is this quantity here called Q star. So Q star is an optimal action value function. Why is this interesting? The action value function lets the agent on the very first time step to do something different from its current policy. So its very first action A is not drawn randomly from policy pi, it's just set by the agent. And so action value functions will be very useful for agents who are trying to control the environment because they allow the agent to understand the impact of different actions on the return. So why are optimal state value functions useful, and why are optimal value functions useful more generally? Well, if you consider this little grid world example here, where you have an agent that can walk around and then on certain transitions it gets more reward. If we are able to estimate this optimal value function V star, then essentially we can extract out of it an optimal policy pi star very easily by essentially just doing one-step greedy action selections. So all of the work goes into estimating V star. V star is a long-term quantity. And with respect to this long-term quantity, then the agent can be very myopic and look at only the next time step. So for example, in the bottom left corner here, where we have V star, we can consider different action choices, and we can see that two actions are tied. So either one of them would be good. But one step over, actually, if we look at the values of neighboring states, the action of going up will be better. And so V star immediately gives us a policy. Value-based methods for control are going to be focused on estimating the value function, and then the policy will just be defined as a side effect of that. And that's the category of methods that we're going to start talking about now. If we have optimal action value functions, it's even easier, because with the optimal action value function, we can just look at Q star, and the agent can pick the action that maximizes Q star, and this will be an optimal policy. Okay, so now how do we get a handle on these optimal value functions? Well, the first thing to do is to try and see if we can set up a dynamic programming algorithm that estimates these value functions, just like we did for policy evaluation. And so over here, we consider the case of V star, and we're just defining what V star is. It's just the best action at every at the particular state S we're interested in. And so this is maximizing over an expectation. And inside this expectation, we have something that should be kind of familiar. It's the immediate reward plus the estimated value at the next state. The only difference here is that the estimated value at the next state is assumed to be optimal, right? So here we have V star, which corresponds to the optimal way of choosing from the next step onward. And we can use the Markov property, which we discussed last time, in order to go from the second line here to the third line, and to essentially write out an equation that relates the value of a state S to the values of its successor states, the next states, S prime. And so now we have a system of equations which can be solved by dynamic programming means. And if we have a discount factor here that is less than 1, we can basically show that we have a contraction property. And so doing this iteration, starting with some value function and iterating this equation as an update rule is actually going to provide a contraction. And V star is going to be the unique solution of this system of equations. So this gives rise to this algorithm called value iteration. It looks very, very similar to policy iteration, to policy evaluation, which we discussed last time, except instead of averaging here with respect to some fixed probabilities given by policy pi, we're going to have the agent always be greedy, so always selecting the action that is currently expected to be best. And so we're going to have a max here instead of an expectation. And we'll see that from a theoretical point of view, this is going to cause a little bit of headache, but we can get around it. Now, what does this algorithm look like when we use it? Okay, so this is a very simple illustration of value iteration in action. This is a simple navigation task where the agent is in this grid. It can move up, down, left, and right, and it has a goal state here, which is marked with a black dot, the biggest black dot. And the agent only gets a reward when it enters this goal state. It gets a reward of +1, and there's a discount factor. And so this essentially expresses the goal of the agent traveling to this goal state as quickly as possible through the maze. And I'm showing here the iterations of value iteration, where we start with the values initialized to 0 everywhere except at the goal state where we have the reward. And so what you see here is that this goal value is propagating backwards from the goal state to the states that are, first of all, 1 time step away, then 2 time steps away, and so on. And so, as you can imagine, eventually, as we do more and more of these iterations, the goal is going to sort of flood the entire environment. Now, what is the policy that the agent should follow? Well, if we are in one of these cells with a circle in it, we should just hop to the neighboring cell that has the biggest circle. Okay, and so if we follow these values, increasing values, we're going to establish an optimal path to the goal. So, okay, now we have an algorithm for computing values. This is requiring us to know a model of the environment. So, one approach could be to estimate a model and then use it. But what I will mainly focus on is how do we do this model free? So without having to estimate the model, but estimating the value function directly. Okay. And most of the time, in fact, I'll talk not about V star, but about Q star, so the optimal action value function, just because this allows us to experiment with the action choices. And so here, I'm just showing you for completeness, the Bellman optimality equation for the action value function. Okay, so it looks just like the one for V, except, of course, now at the very first time step, we always choose action A. So A is fixed, okay? And from the next time step onward, we will do the best thing possible. So on the next time step, we have a max over the possible actions that the agent should do next. And again, this is a nonlinear system, but because gamma is less than 1, we have a contraction property, so there's a unique solution, and we can use a value iteration approach to get it. There's also another approach, okay, to obtain this, which is policy iteration, and this is going to be at the heart of algorithms like policy gradient, for example. In policy iteration, what we do is we start with some policy, we compute its action value function qpi, and then we're going to modify the policy to become better, okay? Now, how do we do the top loop? Well, we discussed this in the previous lecture. There's various algorithms, Monte Carlo, temporal difference learning, n-step, eligibility traces, any of these things would do, right? So I'm going to consider the top arrow here solved from methods that we talked about last time. The bottom arrow says make the policy be more greedy with respect to the current action value functions. And so this is going to be the policy improvement step. And what it means is that the action that we decide to take should be a maximum over the possible actions according to the agent's current estimates. Now, because these are just estimates, so they're not perfect, we are actually going to need to explore also. And so that is going to become an important problem to talk about. So the approach of doing value function approximation in the control setting, generally speaking, is going to be that we're going to have some states. We're going to have an action. This comes as an input to a function approximator that estimates typically q hat, okay? And this approximator will be trained with a target, ut. And this target essentially is going to be some version of sampled return, okay? Could be one step, could be n step. But these returns now may need to take into account the fact that we don't have a fixed policy and we're in fact trying to encourage the agent to take optimal action. So we'll have to redefine these a little bit. Okay. Now we discussed the need to explore, okay? This is because the agent, if it's taking the greedy action, it's just exploiting its current knowledge, but its current knowledge may actually need to be updated and improved. And so the agent may need to take actions that are not fully optimal. And so, in fact, the agent may need to continue exploring forever in the case where it's in an environment that might be changing over time, or if the agent itself perhaps is changing over time, right? The agent's actuation might change, for example, in a robot because of wear and tear. And so exploration will tend to be persistent. Exploration is a very big topic. There's been lots of work dedicated to this. There's, roughly speaking, 4 types of methods that are used for exploration. And I will discuss the first one in a bit more detail because it's just the easiest, but just to make you aware of all these things. The first approach is just randomization. So that means we're going to add some noise on top of the greedy action selection. So epsilon greedy falls in this category. We'll talk about it in a minute. The second very big class of methods is optimism in the face of uncertainty. This means that if the agent is uncertain about actions, it should pick them more, okay? And so this will drive agents to parts of state space that they have not experienced before. Of course, it's a little bit risky to do this, right? Because you might walk into a pit or something like that. But from the point of view of covering the state space, this is actually a very good idea. The third class of methods is what people call probability matching. And so the idea is if we could estimate the probability of each action being the best, then we should take actions in proportion to those probabilities. Okay, and so if an action has a 10% chance of being best and another action has a 12% chance of being best, they should be taken with very close probabilities. So Thompson sampling is a typical example of this approach. And again, there's many different versions of this idea that exists both in Markov decision processes as well as in a simplified bandit setting where the agent just experiences the same state over and over again. And then the final class of approaches, which is in fact perhaps the smartest, but also the hardest computationally, is for an agent to actually plan to get information, so to plan to explore. And so what this means is the agent has to consider explicitly the trade-off between how much reward it might get from an action and what's the information gain in information theoretic terms that it might expect to get from an action. And there are, of course, ideal solutions to this, which are Bayesian solutions to consider the space of all possibilities, all possible actions, or possible outcomes, and try to then approximate the space. And then there's various approximations that people have tried. This is a category of methods called Bayes adaptive MDPs. And while this approach is, in some sense, conceptually the best, from a computational point of view, these methods tend to be very expensive. And also when the agent does not know very much ahead of time, for example, does not have very good priors, it may be hard to apply these methods. So what's randomization? It's the thing that most people do the very first time. Okay, it just means we're going to inject a little bit of noise in the action choices, and that's going to be done according to this parameter here called epsilon. So we're going to, every time the agent has to act, we're going to flip a coin with probability 1 minus epsilon. The agent's going to do what currently appears to be best, so the greedy action. And with some probability epsilon, it's just going to explore, and we can make that exploration, for example, uniformly random. It's a very simple way to balance exploration and exploitation, and it's controlled by a hyperparameter epsilon, which now is going to have to be set somehow, right? For example, we might need to do some hyperparameter optimization empirically in order to set it. If we want the agent eventually to converge to a deterministic policy, we'll have to take this parameter epsilon towards 0 over time. So maybe decrease it according to a schedule. What's the impact of exploration, and what's the impact of this particular parameter? Well, this is a very simple illustration, in fact, from a bandit problem. So epsilon equal to 0 means the agent is always acting greedily according to its current value estimates. And you can see that that's really a very bad idea, because if the agent happens in the first tries to get a good reward for an action that is suboptimal, that agent will never get out of this suboptimality. And so its performance is going to be pretty poor. And otherwise, positive values of epsilon help the agent to learn better. Now, there's also a difference between the top graph and the bottom graph. The top graph is showing the average reward as it is obtained by the agent. And the bottom graph is showing the percentage of time that the agent would be choosing the optimal action. And so one thing that you can notice is that the more the agent explores, actually, the quicker it finds the optimal action. And so its percentage of time that it's taking this optimal action actually goes up. But of course, it's also exploring, and so the reward is not going to be perfect, right? The reward is still going to have some problems. Okay, so now let's try to take this idea and embed it into our first control algorithm that is value function based, which is called Sarsa. Okay, so in Sarsa, we're going to combine two ingredients. One will be estimating the value function, and the other one will be exploration. And so in order to estimate the value function, we're going to use an on-policy temporal difference learning kind of approach. So if we look at the learning rule here, we have a reward, and we have the value of the next state and action pair, Q st plus 1, AT plus 1. Now, what is this value? Well, this value is an expectation. And because we see here AT plus 1, right, and we know we're trying to do control, this means that the action has to be selected from the agent's current policy. So if the agent is using, let's say, a mostly greedy but randomized policy, you imagine this action AT plus 1 as being selected from that, okay? And then this gradient term is just because we're doing a semi-gradient kind of method, right? And so we're asking the agent to update its parameter vector at the input corresponding to the current state and action pair. So on the face of it, this looks just like temporal difference learning, but we have Q values, and we have this further piece of information we need to remember, that the action choice has to be near greedy with respect to the current value estimates, but it's not going to be fully greedy. And so as the agent is learning new estimates, its policy will change. And this will create a kind of non-stationarity that the agent will need to cope with. Now, this is a summary of the much wider sort of general class of semi-gradient methods for on-policy control, of which Sarsa is an example. And so here, the agent is estimating, again, values. Q hat of SDAT is the current estimate of the value function. The value function is parameterized by a parameter vector theta hat. And the agent is going to update its parameter vector theta towards a particular update target. And now we can make a whack load of algorithms for phrasing this target, right? So for example, this target could be a full return, in which case this update is mostly like Monte Carlo. It's called Monte Carlo on policy control. It could be a one-step TD, which is what we saw on the previous slide. So that's like Sarsa. It could be actually some kind of expectation here. So instead of drawing an action at the next state, we could in fact do an expectation over the actions at the next state according to the agent's current policy. Okay, so that's what people call expected Sarsa. We could do dynamic programming updates. And so we can do n-step updates. So we have a lot of freedom in choosing now this update target. What remains constant between these algorithms is, first of all, they all estimate action value function. And second of all, they do this by acting near greedily with respect to the current value estimates. So what we mean by on policy is the agent really acting according to its current estimates. And this is just an illustration of why we may consider varying this target. So this is n-step Sarsa, using the idea that we discussed in the previous lecture of using n-step returns rather than single-step returns. And you can see here some plots showing that there are some benefits for intermediate values of n, okay? And this is essentially because of considerations that we discussed yesterday, that doing n-step backups rather than single-step backups allows an agent to trade off bias and variance, perhaps in a better way. Okay, but just to be very clear, if we want to experiment with different targets, the algorithm stays the same, right? So if you're coding it as one line that changes in this whole algorithm, which is how do we compute this target? So in the on-policy case, control is actually straightforward. If we look at these algorithms, they're very close to what we saw in the prediction case. There are formal results for linear on-policy algorithms, so algorithms that use linear function approximation. Essentially, these bounds show that these algorithms will converge near a good solution, but they might chatter in that space. Okay, so chattering means the algorithm jumping between different values of the parameter vector. And the other thing that we know about these algorithms is that they do depend, the sort of getting to a good region does depend on the exploration, and oftentimes requires very conservative exploration. So starting very randomized and annealing the randomization over time, but very, very slowly. Nonlinear case is still pretty much open. So the existing results are on policy and linear case. Now, there's another algorithm, which is actually from an empirical point of view, perhaps more popular, called Q-learning. And so we're going to talk quite a bit actually about Q-learning and its different versions. And this algorithm is starting from the value iteration equation for action values, which we have written up here. This basically is an expected update. And so the idea always to go from something like an iterative dynamic programming algorithm to a learning algorithm is that wherever we have expectations, we're going to draw samples from those expectations. So to go from this dynamic programming update to Q-learning, we're going to sample this expectation over next states, draw some particular next state that the agent arrives in, and then we're going to update with the estimate from then on. Now, what's the estimate from then on? Well, this involves actually the agent imagining itself doing the best thing from the next state onward, okay? So in the dynamic programming update, we have this max over the next action. This is going to carry over to the update target that is written further down on the slide. This update target is going to be maximizing over the action that the agent should take at the state that it happened to sample. So we're sampling the reward RT+1. The agent arrives at the state ST+1, and it imagines itself doing the best thing possible from then on. Now, the agent is not really going to do this greedy action. It's going to explore from the next state on. But it can imagine itself doing the best thing possible. So this is the kind of algorithm that we call off policy. The agent is updating according to something it's imagining in its head, some different way of behaving, but actually it's going to carry out a behavior policy, which could in fact be very random, could be in fact be uniformly random. Okay. Now, you can see that this might be a little bit tricky, okay? If you imagine yourself, let's say, wanting to change some kind of lifestyle habit, right? What does this agent think in its head? It's thinking, oh, today I'm doing whatever action I like to do. I'm going to get some reward, but from tomorrow onwards, I'll do the best thing possible, right? And then tomorrow arrives and maybe I still don't do the best thing possible. So the trajectories that the agent is taking in its head could become quite different from the trajectories that it's observing in real life. And so from a theoretical point of view, that is both really good as well as it could be really bad. Okay, so the really good part is that when the value function Q here is represented as a table, so where every state action pair has an entry and we maintain separately estimates for it, then actually the agent can converge to the best way of behaving regardless what the behavior policy is, so long as it is sufficiently exploratory. So even if an agent behaves uniformly randomly, eventually it will converge to Q star. Okay, so that's a very exciting kind of property. Unfortunately, when we go to function approximation case, theoretical results are at the moment quite negative in the sense that these agents can diverge with function approximation, even in simple settings like linear function approximation. However, from a practical point of view, empirical results with this type of algorithm are very, very strong, while also relying in some sense on some tricks and extra things to get the agent to work in this setup. So just to contrast a little bit Sarsa compared to Q-learning, okay, so this is a illustrative example from the reinforcement learning book called the Cliff World. So here you have an agent that starts at the start state, has to go to the goal state, and there's a cliff here. So if the agent steps off the cliff, it dies, and there's a big negative reward. But the world is deterministic. So if the agent knew the optimal path, it could actually go sort of very carefully hugging the cliff and get to the goal state, and that would be the best, right? That's the shortest path. Now, what do these agents learn? Well, Q-learning is going to eventually learn this optimal path, but it will fall off the cliff a lot because it needs to take exploratory actions. Exploratory actions might lead the agent to step sideways, right? And then it dies. Sarsa, on the other hand, updates on both good actions as well as bad actions. It updates with all the rewards that the agent is receiving, not just the max, okay? And so it learns to take a roundabout path, right, which is perhaps a safer path. And so this becomes reflected in the rewards per episode that these agents are obtaining during learning. So you can see Sarsa getting better rewards. This is because it's happened upon a conservative path, which is not falling off the cliff, even if the agent is doing exploratory actions. The agent really has to do a few exploratory actions in a row in the wrong direction in order to fall. Now, if we froze the Q-learning policy at the very, very end of learning, the Q-learning agent would do great, okay? But during learning, it falls a lot, and so its reward becomes less. And also, this may slow down learning because the agent does not get to see the good reward at the end of this path, okay? Because it doesn't actually make it there. So this is just to contrast a little bit the on policy versus the off policy distinction. So now I want to tell you a little bit about versions of Q-learning that work in exciting ways. So the first thing that we'll talk about is DQN, which is the algorithm that has tackled the Atari games. We discussed a little bit the example of the Atari games last time. This is really pioneering work done by DeepMind. So in this case, we have an agent that learns to play video games from raw pixels just by playing, just by interacting with the game and observing the scores in the game, not by prior knowledge. Now, because we want to interact with the game, we need to have a neural network inside of the algorithm that is capable of generalizing well from images. Okay, and so this is why here we observe a convolutional neural network architecture for the beginning layers in order to analyze the image, and then towards the output we have some connected layers. So these connected layers are helping now the value function in its estimation process. The other thing that we have here is a stack of previous frames. Now, the reason for this is that just one frame does not give the agent full information. For example, the agent can't tell which way things are moving or how fast things are moving if it looks at only one frame. It needs to look at multiple frames. Otherwise, however, aside from putting in an architecture here that has some intuition about the domain, the way that we're going to update parameters is by Q-learning. Okay, so this update rule here, you're going to recognize it as a semi-gradient style update with a target that is a Q-learning target. Now, because we have a deep network in here, we may want to play a few more tricks, let's call them, in order to stabilize the updates. And this is because, as I've mentioned before, Q-learning with function approximation can have some problems. And so one way to think about the kinds of things that we're going to do is that we're going to try to eliminate the non-stationarity caused by the reinforcement learning algorithm. For example, the non-stationarity in these targets that have the current estimator in them. We're going to try to make the setup as similar as possible to the setup that we have in supervised learning. So just to sort of reiterate, what this algorithm is going to do is to learn to play the Atari games on the Atari game console from pixels, mapping onto Q values, which will then be used to decide for the agent to decide what to do. Okay, so what are some core components of the algorithm? One of the tricks that we're going to do is to make the target more stationary, okay? And so this is done by using target networks. What this means is that we're going to take a clone of the deep network inside the agent's head. We're going to freeze it for a little bit, and that's the network that is going to provide these targets. So the target is not with respect to W, the current version of the parameter vector. It's respect to a past version, W minus. Okay? And so this will provide stability in the output. And every so often, some number of trials, we're going to take the current target and make it a target, and then we're going to continue training with the current network. So we are always updating the target, but keeping it fixed while Q-learning is going. The second trick that we're going to use is actually a long sort of discover trick that came from the reinforcement learning from robotics literature, which is experience replay. So what this means is an agent is going to remember its tuples of experience, S, A, R, and S prime. It's going to put them in a big buffer. And whenever we train, we're going to take transitions from this buffer and apply this update rule with these transitions. Now, what this does is that it breaks the input sort of dependencies between successive states. Rather than always updating from a state ST and then next to a very correlated state ST plus 1, we're going to update at states that are from all over the environment. And so this is going to be more IID in terms of the input sampling for the agent. And then, of course, we're remembering our experience. So this means that we can revisit transitions, and we're going to see in a minute that we can make that process, in fact, a little bit smarter. Okay. So the target network intuition is that we want to make sure this network does not end up chasing its own tail because of the bootstrapping, because it's using its estimates. It's more actually useful for smaller networks than it is for bigger networks, in fact. But it proves to be quite a useful trick. And then the other thing that I want to mention is that there's actually lots and lots of other improvements that have been made to DQN and can be made to DQN. And I'm going to talk a little bit about a couple of these things, specifically double Q learning and prioritized replay, because they're perhaps the most useful. So prioritized experience replay has to do with the organization of the replay buffer of the agent. And in particular, if we have many transitions and the number of transitions is growing, how do we want to pay attention to these transitions? And one sort of intuition is that we would like to learn a lot from each transition that we experience, that the agent experiences. And so if a transition has the potential for the agent to do a big update, right, like this is what it means to learn a lot, we would like to prioritize it more. So this will drive the agent to sample more state action pairs at which it could make a big improvement. And so we can do this essentially by prioritizing transitions in the replay buffer according to their current estimate of this Q value error, right? This TD error between the current state action pair and the next step. And empirically, this actually helps quite a bit. And so if we look at these plots, these are showing mean scores, normalized mean scores for some games. And so we can look at a uniform organization of the replay buffer where we sample everything with uniform probability. And then we can look at different ways of prioritizing according to the TD error. So for example, in proportion to the TD error, or just by ranking, and then going with probabilities derived from the rank. And in both cases, this helps the agent learn a lot faster. The other interesting aspect is that Q-learning actually has a maximization bias that can slow the algorithm down sometimes. And so this is one example here. It's an interesting example where the agent has a start state, okay, A, and it has two actions. One is the right action, which gives it the reward of 0 and terminates the trial. The other one is a wrong action, but it goes to a stochastic state where the mean of the reward that will be obtained is actually negative. So it's not a good idea to go to the state B. But of course, we have variance because the rewards are drawn from some distribution. And so sometimes you will get a positive reward just because of this variance. And if the agent gets a positive reward, it can start being deluded into thinking that B is a good state. And because Q-learning is updating with a max, okay, then it can decide to go to the state more and more. And in fact, it can take a very long time until it realizes, oh, the state is actually negative mean. And then it starts going back towards the optimal. And so double Q-learning is an approach that was developed by Hade van Hasselt, which is trying to break this sort of optimism of the agent, essentially by using two action value functions, Q1 and Q2, which get updated on independent time steps. And at every time step, we're going to pick one at random to update it, and we'll update it with a target that is computed with its suggestion of the best action, but with a value that's coming from the other network. Okay. And so I'm thinking, what's the action that I want to do? But I'm asking somebody else's opinion about the value of this action. And because we have deep coupled updates, essentially, the networks will become a little bit less optimistic than in one sort of in the regular version of Q-learning, and the maximization bias gets removed. So it's an interesting algorithm. Interestingly enough, of course, this was done in the tabular case, like very early on, like 2010, and nobody cared at the time. Because it made some small improvements, but then the big gains only became apparent with deep learning and with DQN specifically. And so I just want to use this also as a little bit of a tale about, sometimes you do some research and it's interesting, and it may only become relevant much later on because the context in which it is used changes. So even if people are not paying attention to your work right now, you don't have to lose hope about that. And so this is just an empirical illustration of double Q learning and the fact that it does correct this maximization bias, and it can make the learning a lot faster than regular Q learning. And so we can add it in the context of DQN. It makes quite a big difference. So this is just an illustration of what it's doing in the context of using it with DQN for returns, but it does always tend to have a stabilizing effect, okay? And if you think about it, why is this happening, right? You can see that these blue curves, which are double DQN, have lower variance than the orange curves, which are the regular DQN. The stabilization happens because the algorithm is not now so prone to latch on to max values, which may actually be sort of very, very inaccurate. Okay. Now, we can add all kinds of these improvements to DQN. And this is sort of a little bit the deep learning story. They all help. And adding all of them can help even more. So there's a lot of tricks here, and we're gonna we're not gonna talk about everything. Rainbow, this highest curve here, uses a lot of the tricks, okay, and it can work very well. Now there's even further follow-up since this. So Rainbow still provided sort of superhuman performance only in a subset of the Atari games. There is now a recent version developed by my colleagues at DeepMind called Agent 57, which does some further improvements and actually has now essentially conquered, in some sense, all of the 57 Atari games. That's what this 57 stands for. And this includes some of the games that are very difficult for exploration. Now, how has this been done? Actually, a lot of the benefits have come from improving the exploration process, because one of the big concerns with previous versions of these algorithms was that if exploration is naive, the algorithm may not get useful reward information early enough. And so one adaptation here is using intrinsic rewards. This means that the agent is picking some things in its environment that are not the usual reward system, but which it may try to either predict or maximize in order to sort of propagate more gradients and do more learning. And in this case, the kind of intrinsic rewards that the agents are using are novelty-based. So the agents reward themselves for discovering new things about the environment or unexpected things. And we can measure novelty in various ways, for example, by looking at TD errors or aggregate measures of TD errors. A second important ingredient is diversity. So what does this mean? It means that we would like the agent to exhibit diverse behaviors and maybe look at different discount factors. So this was a question actually that was asked in the previous lecture about the role of the discount factor. Sometimes if we have agents that generate policies that optimize many different things and for many different horizons, these policies, on the one hand, are coherent, right? Because they're optimizing for something. But on the other hand, they can also be very different from each other, and they can be called on in different parts of state space and improve exploration. And then finally, there's an adaptation process. And so there is essentially a decision maker on top, a policy on top that decides which behaviors to use, depending on the agent's current state of knowledge and on the part of state space that the agent is in. And so with all of these things, we obtain this kind of curve here at the top that is doing very well. A couple of other things that the agent is doing that I just wanted to mention. One is that when we assess novelty, there's two different kinds of novelty. One is short-term novelty, right? So immediately I see something that I did not expect. The other one is long-term novelty. Now, short-term novelty in some sense can be prone to disaster, right? So if, for example, you have an agent and there's a noisy TV in the room, you can have this problem that the agent becomes fixated on it. But this problem can be solved if the agent is also assessing somehow long-term novelty, and there's a way in the architecture of this particular agent to combine these two aspects. And in this case, we're sort of doing this assessment also through a memory process that is done in the network. The other aspect here is that as I mentioned, we're going to have some combination of extrinsic and intrinsic rewards that generate a whole diversity of policies. So we're going to have agents that take the extrinsic reward, this is the reward from the task, and take some intrinsic rewards that are coming from this novelty system, and then combine them with different constants here, with different factors, and also use different amounts of discounting. And so this is how we're going to generate actually a whole bunch of policies and a whole bunch of behaviors that the agent can use in its discovery process. So I'm going to stop here for a minute and ask if there are questions. This pretty much wraps up the discussion of value-based control methods, model-free.
Yeah, there are a few questions. Perhaps we start first with a question about dynamic programming. So Pierre asked, in the Cliff example, why do dynamic programming, an algorithm that starts backing up from the terminal state, is more costly than a graph search method that starts from the initial condition?
So if we did dynamic programming, we can always start, if we have a terminal state, we can always start from the terminal state, and actually we can do things quite efficiently because we can now prioritize, again, like if we're thinking about the order in which we're doing updates, we could actually prioritize states in order of their distance, backward distance from this goal. Okay, and so that's an approach that's actually been explored by Moore and Atkinson. It's a form of prioritization that is actually quite similar to the idea that's used in the prioritized experience replay buffer. Now, not all problems are goal-based, right? Some problems have a general reward function, and then it becomes less clear where we should start and how we should do these sweeps. The second aspect of it is that most of the time we will not assume that we have the model of the system, and estimating the model of the system in order to then use it for dynamic programming may actually be costly. So model-based RL is one of these areas of research that I'm both very excited about, and I really wish it would work better, right? And when you're doing things like value iteration, you really observe that if you have models that are imperfect, using dynamic programming at all, whether forward or backward, can be a problem. The other thing that I will say is that if you want to do things backwards, so if you want to start at the goal and then update things sort of backwards from the goal, you need not just the forward model, so going from state action to the next state, but you actually need the backward model, right? You need to be able to determine what are the predecessors of a state. And while that is fine when your model is given, actually learning that from data can be more involved than one would hope. And in fact, we have a submission to NeurIPS with one of my PhD students that discusses that issue. I'd be happy to talk about that to Pierre further later on.
Yeah, cool. So I think he also have a secondary question, which says, how would the uncertainty in the environment affect dynamic programming?
So dynamic programming, if we have a stochastic model, should work fine even in when we have uncertainty, when we have stochasticity in the environment. If we have uncertainty, but we don't know the distribution, right? So it's sort of like, let's say we don't have even like a prior over the model. We're not really maintaining one model, but we have some uncertainty bars on where the transition probabilities would be, for example. There's a framework called Robust MDPs that deals with that case. And so one can do dynamic programming in that framework. It becomes computationally more expensive because now we have to essentially do min-max optimization, right? So you kind of pick the worst case and you optimize with respect to that worst case. And also the solutions that are obtained are a little bit more conservative, perhaps, than one would desire, but in practical applications, that can be a useful approach as well.
Mm-hmm. Okay. Lastly, we have another question. So do we have any theoretical guarantees that intrinsic rewards would not lead to a very bad policy?
No, we don't. And so intrinsic rewards are a concept that, of course, comes from psychology. And, if we relied on intrinsic rewards to sort of in large extent, there is the potential that they pollute the real reward sufficiently that we can't really find an optimal policy anymore. So that leads to three potential follow-up thoughts, right? One is that we can play a game that's a little bit like what's described here in Agent 57, where the intrinsic and extrinsic rewards are mixed in various proportions. And we maintain all of these behaviors, and ultimately there is some other sort of value function that the agent is going to learn that's the real value function that's driven just by the real rewards. And so the intrinsic reward plays a role in the exploration process, but does not end up polluting really the true single value function necessarily that this agent has. A second thought is maybe we can actually discover some nice intrinsic rewards that would fulfill their goal without leading the agent into bad solutions. And there's been quite interesting recent work, for example, by doing meta-learning to learn these intrinsic rewards if we might have a distribution of environments. But in general, this is, I think, quite an open problem. Like what represents a good structure for these intrinsic rewards?
Okay, I think these are all the questions for now.
Okay.
Thank you.
So we're going to move on to discussing policy-based approaches. Okay, so far we've talked about action value methods that learn the value for every action, and they then pick the max, right? So the value function is parameterized, and the policy is obtained as a side effect of the value function. Okay, policy-based approaches. The idea is that we're going to parameterize the policy directly. Okay, and this is going to be a stochastic policy now because we need to get exploration going somehow. But there will be parameters that define the policy, and we're going to want to optimize these parameters directly in order to optimize return. And so there's a vast class of policy gradient methods that people have developed to do this kind of thing. And one way to think about it is that while the previous class of methods was based mainly in value iteration, this class of methods is mainly based in policy iteration, right? So we can think of these methods as some form of approximating policy iteration, where the policy is an equal citizen, right, to the value function, and it's also parameterized. And so we're going to talk about a few of these algorithms. There's actually quite a bit more work that I won't get to talk about. I'm trying to cover algorithms that are sort of at the base of many different methods. Now, why might we want to parameterize policies rather than value functions? In some cases, the policy is just simpler to approximate than the value function. So I mentioned in the previous lecture this example where we were working with Hydro-Quebec. That was an practical application, where the policies they were interested in were all linear threshold policies. Like you have some variable, you start it at 0, you ramp it up, and then you decide where to stop ramping it up. And so the policies are very simple, but maybe the value functions are very complicated. And then actually, in some cases, even the optimal policy is stochastic. And so, for example, if you're playing poker, you never want to play deterministically because then people take advantage of you. So there are cases where there's partial information in the environment, or maybe there's multiple agents in the environment, and you want the policy to stay stochastic. And also a very important application area is continuous action. So for example, if you have robotics applications, the space of actions for the agent may be continuous, and then doing a max over a continuous action space can become quite problematic, right? We either have to sample the action space, or we need to run some kind of continuous optimization, even on a single time step to do that update, whereas with a policy, we can handle that quite easily. And so in order to illustrate sort of the basic idea, I just want to show you a very simple case, which is what people call a gradient bandit algorithm, okay? So there's no state here, just action, all right? We have some preferences over these actions. So HT here is a preference function. It doesn't have to be the action value function, it could be something else. right? It just tells you how much you prefer different actions. And so now we can parameterize the policy based on this preference function. Okay, so the policy here is actually exponentiating these preferences and then normalizing, right? Very standard trick. So I think of these preferences essentially as potentials. And now we use Boltzmann. And so now there is going to be no value function. We're going to update the preferences. These are the parameters of the policy. Okay. How do we update these preferences? Well, we're going to take a gradient with respect to the reward, because in this case, we're trying to optimize the reward. And there are a few slides here of math that are showing that, which I'm not going to show you in detail, but I included them for completeness. Okay. It's more interesting perhaps to look at what this update rule looks like. Okay. So first of all, we're updating preferences between one time step to the next. There are sort of two parts to this update. The first part is like a sort of TD-like error, maybe, right? It's saying, if I were to maintain an average of rewards overall, RT bar is this average over all the rewards that we're getting, and now I'm getting a new sample of reward RT, how much better is this reward than the average? Okay, and so if this reward is higher, then I'm going to prefer this action more. And if it's lower, I'm going to prefer it less. And then the second part here, this whole little bit here, is basically just taking the gradient of this policy with respect to the preferences. Okay, so we're just going to use gradient-based optimization for this. And so now here is, just a simple illustration of this algorithm in action on a bandit problem. This is taken from the Rich Sutton book. And so here we're looking at this algorithm with different learning rates, right? Learning rate matters. But there's two different interesting versions here. One is the blue one, and the other one is the brown one. And you can see that the blue one is much better. Now, what does the blue one do in addition? Is it uses a baseline. So it subtracts out of these preferences some target value, okay, which essentially can be used to rescale, right? So this is a standard trick if I want to lower the variance of the updates, for example. And baselines can really be anything that is action independent, right? So something like the average reward received over time is a baseline. But you can come up with other baselines, and there's a literature on different kinds of baselines as well. So that can really provide much faster learning because it reduces the variance in the updates. Now, this also tells you that these preferences don't have to be Q values, right? Because if I'm starting to subtract things arbitrarily, obviously we're not going to converge to anything that's accurate Q values. And so policy-based methods don't have to estimate accurate Q values. Even if they estimate a value function, this value function only needs to be strong enough to point the policy in the right direction for the gradient. Now, here are some examples of policy parametrizations. Okay, so here we have a linear setup where we have a state action feature vector phi of SA, and we can consider a linear preference function on top of this feature vector. And so now we can take a policy, and again, we take these preferences, we exponentiate, and we normalize. And so if we take a gradient here, actually the gradient comes out pretty nice, okay? The gradient is just the feature as the current state action pair minus this sort of normalization, which you can think of as the average feature, okay? Averaged according to the policy. So this is useful, for example, in the case where we have discrete actions. Now, if we have continuous actions, then maybe we want to parameterize the policies using some kind of Gaussian distribution, okay? And so maybe we want to do a parameterization that's what we call linear Gaussian, okay? So what does this mean? This means that we're going to have at every state, okay, we consider the policy to have a Gaussian that has a particular mean and a particular variance, okay? The mean and the variance are shared across state space. So they are the parameters of the policy they're going to be estimated, And there's going to be a feature vector here that does depend on the state that allows the system now to essentially have a different mean and a different variance at every state, but to have these estimated by these shared parameters, theta mu and theta sigma. Okay. So now the policy at a particular state is going to have a Gaussian form. And of course, we can take a gradient of this policy with respect to theta mu and theta sigma. And we can then determine these parameters that optimize for return. And of course, if you have some other favorite way of parameterize a distribution that can generate continuous actions, you can use that, right? The main constraint is always going to be, can we actually take a gradient? And that operation, mercifully, is quite simplified these days in a lot of the machine learning, deep learning software. So here's just for illustrative purposes, the gradient of a Gaussian policy. So now let's talk about the policy gradient, okay, overall. So what's the idea? The idea is we're going to have a policy. It's parameterized by this parameter vector theta. We're going to take the gradient of this policy, okay, with respect to the parameter vector in order to optimize the return, okay? So what's the return? The return denoted here, eta of theta, is just the value function of this policy with respect to some distribution. Now, this sum distribution bit becomes quite important because we want to be able to compare policies on an equal footing, okay? And so this is the subject of quite a bit of research, in fact. One way to think about it is that we'll fix an initial state distribution, and we're going to sort of be interested in this objective with respect to that state distribution. A different way to think about it is that at the current policy, we consider the stationary of that policy, and we want to update with respect to that. Once we've fixed our objective and it's the value of this policy we're trying to estimate, sort of to optimize the return, we can now just do stochastic gradient ascent. So this is the usual rule that says we're going to optimize our objective, right? But the gradient itself actually has a little bit of an interesting form. And again, like this is given in the policy gradient theorem, and there's some algebra to go through. It's a little bit like the gradient bandit one, okay? And so it's an exercise that you can do on your own. The shape of the gradient, however, is actually quite interesting. It's basically averaging over the distribution of states that we're interested in. It's having the estimated returns for this distribution. So Q pi here is the true value function, and we can use here either returns, okay, as a proxy for this, or we can possibly use an actual sort of parameterized value function. And then we have this term here, that's the gradient of the policy. Okay, and we can derive all kinds of algorithms from this. This is a derivation particularly for reinforce, which is currently very popular. One way to think about reinforce is that it is the Monte Carlo version of the policy gradient theorem, okay? And so we're going to update the policy in the direction that's indicated by the return, full return. And so in this case, we never actually have any value function whatsoever that we're estimating. We just get samples of return, and in principle, at every step, we can update the parameters of the policy using this rule. Now, as discussed before, we can also actually use a baseline, okay? And so we can decide to offset all of the action values, for example, by some amount, which is denoted V here, that is independent from the action. It could be something like the average Q value, right? So the value function over the state S, or it could be something else that we actually design. And this is essentially going to help reduce the variance. One of the particularly popular approaches to this is to not use reinforce, actually, so not rely just on returns, but try to still leverage some form of value function approximation. And so this is the idea depicted here. This is what's called an actor-critic architecture. So in actor-critic, we have a state that's coming in. The state is given both to the policy and to the value function. The role of the value function here is essentially to provide a learning signal to the policy. And so, for example, the value function might provide a TD error to the policy or an n-step TD error, right? So any of the value function kinds of errors that we normally have talked about in the case of prediction, we can take it and provide it to the policy to help the policy improve. But the value function and the policy are independently parameterized. Now, what this means in practice is that, for example, we might have one deep learning architecture, and there may be some value heads and there may be some policy heads, but there's a shared layer of features. So oftentimes, even though we think of this as they're independently parameterized, actually the features that they're working with may be shared. And so we can have various kinds of actor-critic methods depending on how exactly we decide to put the reward or the return in here. One other thing that I was going to mention is that there are some complications when we're using sort of discount factors with these kinds of methods. And Phil Thomas at UMass has been exploring that, like what's exactly the right gradient when we have discounting. If one uses something like total reward or average reward, that problem goes away. Okay, now let's look again at some practical, very successful incarnations of this approach. Okay, so one incarnation is what's called advantage actor-critic, or A2C. Okay, so the core idea of A2C is that we're going to use as targets, okay, in the policy, the differences between something like an n-step return, okay, which is depicted here, and the current estimate of the value function. So the value function becomes a baseline. And so the quantity that's driving the learning is this thing called the advantage. Okay, how much better would I be with some different action than I am on average right now? Okay, and so if actions have a positive advantage, thinking back to the gradient algorithm, their preferences will be increased, right? And the policy parameters essentially will capture those preferences. These actions will become taken more often. So now what's the A3C here? It's an algorithm called asynchronous advantage actor-critic. And the idea here is that we want to get these agents enough exploration. And one way to do this, if we can work in simulation, is actually to clone the policy and run many threads that are all producing data and then aggregate their updates. Okay. So this is a way to get around the exploration problem. For example, if I have something like a robot simulator, we can start the robots in different parts of state space. And even though they have the same policy parameterization currently, they'll generate different trajectories. This will provide varied data to the learner, and the policy gradient perhaps will be more informed, and the signal in the learning process will be strong. And so these are some examples, okay, where we have A3C here. This is the yellow curve, okay. We're looking at some specific Atari games. DQN is this blue line here at the bottom, so vanilla DQN not doing very well. And then we have some sort of further improvements to this algorithm by, for example, doing on-policy learning like Sarsa, or doing n-step and so on. But you can see that by and large here, A3C is doing very well. Now, if I were to flip to a few slides back where I was showing you rainbow, you'll also see an A3C curve there, and A3C there is not doing that well. Okay, so overall, you can't say that, let's say, policy gradient methods are always dominating value-based methods like Q-learning or vice versa, right? These are different methods that we have in our toolkit, in our arsenal. And which one does better oftentimes depends on the environment and other external issues, like how good we are at choosing the function approximation and other tricks, right? Like using the intrinsic rewards for Q-learning helps a lot. And so at the moment, don't think of this as one of these methods as a clear winner. Think of this as alternatives that we may use for different kinds of applications. Now, we can revisit the policy gradient objective and try and do a few more things here, okay? So one idea that actually, again, has been explained in early work by Shamkakade, for example, on conservative policy iteration, is that if we are collecting data with some policy, call this pi old, we may not want the new policy to be very aggressive in terms of moving away, right? So the intuition is, if I have some policy that's visiting this part of state space on the right-hand side of the environment, and now I want to update it, the new policy may go to some parts of state space I've never seen before, I've seen very little, right? So maybe I'm driven there because I'm optimistic, but maybe that's a terrible idea, right? And so these kinds of algorithms essentially try to help the agent not stray too far from the places where it already has data, okay? And so in this case, for example, we have here sort of like a surrogate objective that is basically saying, let's think about the advantages according to the old visitation distribution pi old. We're going to adjust them for the new policy pi, the new version of the policy that we would like to do. And so this is going to be sort of reshaping whatever old advantages we had into the new distribution that we are considering. And maybe now this becomes our objective, okay? And so this allows us also to reuse past data. In fact, we can reuse a lot of past policy data just by sort of reweighting it with respect to the kind of policy that we're thinking about now. And so this leads to a class of algorithms called trust region policy optimization, or TRPO, okay? And so in TRPO, we are optimizing this particular objective function that is reshaping the old advantages, reweighting them according to the current policy. And it's also telling the agent, don't stray too far from the old policy because you have no idea what's going on if you go very far, right? So this is expressed here as a KL constraint between the old policy and the new policy. And delta here is, think of it as a parameter that quantifies how much constraint we want to have. Now, of course, this data here is going to be estimated empirically. So we'll take whatever samples have been drawn from this policy pi old and we'll estimate the loss. And, you know, in terms of the mechanics of the algorithm, this particular version of it uses conjugate gradient in order to solve the optimization. So this is work by John Schulman and colleagues. There's a different version of this algorithm called PPO, proximal policy gradient. Very popular right now for all kinds of dynamical system optimization tasks, the Mujoko kinds of tasks that are available in the GIM simulation environment. So here, instead of doing a constraint optimization, we just do the Lagrangian form, right? So we take this constraint and we just put it together with the rest of the objective. And we have a beta parameter here that mediates between the two. And compared to the previous version, this version does two changes. One is it uses just stochastic gradient descent, so not conjugate gradient for the optimization. And the other thing is that it twiddles around with this parameter beta, okay? And so what this means is that we are sort of trying to make sure that the agent is not too conservative, not staying too close all the time to the old policy. And so we can allow the beta to vary based on these estimates of the KL distance. Okay. And so this has empirically very similar performance to TRPO. It's much easier to run. It's one of the reasons why it's very popular. Is it's a good entry point into policy gradient methods because it's simple to implement and it can be unstable, but it's actually really easy to work with and reasonably efficient. And it's been used in all kinds of locomotion tasks. I'm using PDF files today because I don't want to have problems with Keynote like yesterday, but you know, if you had the videos, you would see these agents walking around and swimming, and you know, the results are pretty good. The other thing that we can add on top of this is some tricks from value-based methods. So this is the deep deterministic policy gradient, or DDPG algorithm, which again is quite popular and almost state of art and in many domains. And in this case, what we do is we are using Q values as targets, and we're using some of the standard tricks that we saw in DQN, using a replay buffer, using a target network, and also using some Polyak averaging in order to do the updates. And again, this has quite good results in a variety of simulated robotics-like tasks, 2D, 3D tasks. And there's been lots of additions and other exciting developments that have happened to the DPG. There's a slew of papers on arXiv that you can look at for that. So just to sort of summarize the work on policy gradient, basically policy gradient is a really general class of methods, right? We can apply it anytime that we can compute the effects of parameter changes on the action probability. So it doesn't have to be an MDP at all, right? Could be any kind of arbitrary environment. We can just parameterize the policy and work directly with that. One interesting application that sort of illustrates that is that it's been used in spiking neuron models. So to model the activity of neurons and to do learning rules for spiking neurons. And, in terms of like what the parameterization of the policy should be, well, this is now task dependent and it's left to the imagination of the designer to decide what a good policy parameterization might be. And I will stop there for a minute and see if there are any questions about sort of policy gradient methods more broadly.
So again, attendees, if you have questions, please type into the chat or raise your hand. So perhaps I can get it started by asking Doina a question. So perhaps let me ask about, just you mentioned DDPG. Is there any verdict about, say, off-policy model-free control? Is it actually theoretically sort of justified that DPG actually you can figure out what's the policy that you don't have yet?
Yes. So there's excuse me. There's an increasing body of literature on this, and off-policy control. So I will try to summarize the current state of the results. Off-policy control can work if you stay close to the distribution that you have seen in the past, right? So conservative helps, and in the case where you're doing conservative stuff, we can prove some results in the policy gradient setting. And policy gradient is easier in some ways to analyze than value-based methods because the parameterization is directly on the policy, and so we have a very direct knob, right, and control in terms of stability. What to do in the general off-policy case is still pretty much an open problem. And also in terms of, let's say, even off-policy evaluation, so figuring out how good a policy is based on a different data distribution, that's actually the topic of quite a bit of existing work and ongoing work. So for example, there's this whole family of algorithms called DICE, dual dice, Agi dice, and so on by Ophir Nahum and colleagues that look in deep detail at this sort of question and use primal dual optimization. Similarly, there's work by Li Hong Li looking at primal dual optimization for doing off-policy policy evaluation reliably. And since, if you think of policy gradient as an approximation to policy iteration, you can see that question is quite important for the setup as well. My bet is that in the next few years, there's going to be quite a bit more of understanding that emerges exactly what are the limits of what we can do in the off-policy policy gradient style case.
That's a great answer. So we have a question. I think this question came first. So it's a bit of a request. Can you talk a bit more about model-based RL and their potential to be more sample efficient?
I will do that a little bit in the next part of the talk. Yeah.
There is one more question, I think, about this part of the lecture. What about the convergence guarantee in policy gradient method, since it is not classical SGD?
Yeah. So policy gradient methods actually have much better convergence guarantees because we can really actually set them up in some cases as SGD. So for example, if we do reinforce, right, with returns, we parameterize the policy, really we're doing gradient update. So that case is very well understood, right, what happens. The only problems occur when we still have these errors coming from a value function estimator, right, which is training over time and which can be non-stationary. Broadly speaking, the kind of guarantees that are easy to obtain are ones that are essentially sort of 2 timescale guarantees, where we say, okay, we're doing policy evaluation. So we compute the value function associated with the current policy pretty well. And then the policy is going to get its gradient, but the policy is still moving much, much slower. And so the value function updates with a high learning rate, the policy updates with a low learning rate. And so if the value function can converge faster, then we can show some guarantees in that case as well. In the linear case, right? Because nonlinear function approximation is like a whole different can of worms. So they either reinforce where we're using just returns, or this case where we're doing 2 timescale analysis. This is all pretty well understood, except for nonlinear function approximation. There, even the 2 timescale analysis has its limits, right? Partly because even the TD, the prediction case, still requires quite a bit of work for that.
Okay, great. These are all the questions for now.
Okay. So now let me talk a little bit about a more loaded topic, okay, which is knowledge. Okay, and in yesterday's lecture, I mentioned AlphaGo and the fact that AlphaGo needs to acquire 2 kinds of knowledge, right? Well, one which is procedural knowledge. So think of the policy, right, as procedural knowledge, how to do things. And then there's predictive knowledge. And so the value function, for example, is a form of predictive knowledge. It tells you something about the expected long-term return. A model would be a different kind of predictive knowledge that talks about what happens in one time step, right? Like what state might I end up in? It's also predictive knowledge. But of course, the way that we've been talking about these things so far, the knowledge is somewhat limited, right? So the policy is for optimizing for a particular task. The value function is the expected return for that task. So what I want to tell you about a little bit is how to expand this and to kind of get at the heart of what it means to have RL agents that have broad knowledge of their work. Okay. And so we're going to focus on these 2 types of knowledge, procedural and predictive. And what we would like to phrase this in a way that is sort of natural from a reinforcement learning point of view. And there's actually 3 things that we would like to have, 3 properties of this kind of knowledge. One is that we would like to express many things, okay? The second one is we want to learn this from data in, ideally in the same way that we learn policies and value functions. And then finally, we would like this knowledge to be composable, okay? So to support, for example, planning, like in dynamic programming. So that's where models fit in, right? Models are composable. You can think of, oh, I'll go 1 step to this other state, and then from there I can do this thing and go to some other state. You can take models of that you have for different state actions and chain them together and consider choices. And the model, through the dynamic programming, approximate dynamic programming mechanism, will allow you to do that. And so we need to think a little bit about how to do this for RL agents. Okay. So one way to express procedural knowledge is through this framework called options, which you can think of as a generalization of primitive actions that allows behavior to persist over time. Okay. And really the inspiration for this comes from older work in classical planning on, for example, macro actions that are just sequences of actions, and also work in more classical control on, let's say, behavioral controllers or existing sort of designing controllers that an agent can use later. So an option is essentially a sub-policy, right? It has a place where it starts, it takes actions for some time, and then it stops according to some termination condition. And this termination condition is a stochastic coin flip that depends on the current state. And so from the point of view of what this does to our framework, conceptually, we move from having a Markov decision process where time ticks, and on every time tick, we take a primitive action, and that one lasts 1 time step, to what's called a semi-Markov decision process. So that means we're at the decision point. This is one of these empty circles. We consider longer term things that we could do. We decide on one of these things, and then it lasts for a while. It arrives at another decision point, and so on. Now, a semi-Markov decision process still has the Markov property with respect to the previous decision point. And so the transition reward, the distribution, and the time distribution are only going to be dependent on the previous decision point and the decision that was made there, the previous option. And so dynamic programming methods, TD methods, all of these things actually all immediately generalize to this case very easily. But if we have an environment where we're building various layers of this, actually we can take advantage of this layering. And so we can devise new algorithms also that know it's not just the decision points, but actually there's many decision points at many different time scales, and we can all relate them to each other. And so I'm going to show you an example here, and we're going to talk through the issue of models on this example as well. So this is a standard sort of illustration called the 4 rooms domain. I've showed it to you before in the value iteration case. You have an agent, it starts somewhere, it has to find a goal state, okay? And so in this environment, we can do value iteration. We have these primitive actions that go up, down, left, and right. But if we don't know where the goal is, it might take a very long time when we're doing exploration, especially at this very fine-grained level, for the agent to make its way to where the rewards are. Now, we could also sort of consider larger jumps, okay? So for example, if an agent is inside a room, the agent might consider going to a hallway of that room. And it might learn that navigation sub-policy within that room. And so we're going to call one of these an option. Okay, so an option starts in any state inside a room, and it knows how to go to one of the hallways of that room. And so now in this environment, we can imagine having this structure where for each room we have 2 options leading to the 2 hallways. Now, these can't really solve the entire problem for us because the goal might be in the middle of a room. So they don't necessarily replace somehow the primitive actions. You can almost think of them as an addition, right? But they do allow the agent to circulate very quickly because one agent can jump from a hallway to a different hallway, right? It already has that policy available to it. So you can think of that policy as a procedural form of knowledge of how to navigate between the different rooms. And so that can help us quite a bit in terms of the exploration, right? So we have some curves here on this graph. These are Q-learning agents. One of them, the top graph here, which is called flat, is a flat Q-learning agent. That's just using its individual policies, okay? The orange line here is a hierarchical agent that's using options, okay? And so you can see that because the agent is able to navigate in this sort of structured way, it can actually figure out the problem quite a bit faster. Now, what's the role of models? Models here can be associated with options, okay? And the model has the same sort of structure that it has a reward and it has a transition probability, but the transition probability is not between successive time steps, is between decision time steps. So if I start at a particular state, what's the distribution of states that I will end up in? And also, how much time will it take me to do that? Okay, and the time is necessary because I might need to know this for discounted environments. And so the model of options has the reward until termination and the discounted transition to the termination state. And so you can think of these models as predictions about the future, okay? And in this case, we have more flexibility in the models because they're predictions about the future over different time scales, right? Over the time scale of the option. And so we can see what happens if we are also using models, okay, in addition to simply using the hierarchical layer here, okay? So what's this blue line? The blue line is an approach that is mimicking the Doina algorithm, where whenever we have data, we use it to update the value function, but we also use it to update models. And then these models are used in approximate planning. Okay, and you can see that there's a gap here. Like if you're using the models, you can actually do quite a bit better than if you are simply using the policies that are resulting. Okay, and so the model in this case does have quite a bit of an advantage. Now, why did I decide not to talk in detail about model-based RL today? Is that on one hand, I really believe that in order to make model-based RL successful, we need the temporal abstraction angle to this, because time step to time step models are just very hard to learn. Okay, in a single time step, there's, especially if you have something like visual observations, there's just so many things that the agent has to deal with, and which of this is noise and which is not can be very difficult. Whereas over an extended horizon, and especially if we structure it, so the agent can't terminate everywhere, it only terminates at a few states, the models become, I think, much more useful. So I still have hopes that model-based RL is going to eventually sort of help us, especially in this hierarchical case. Now, also the other reason I didn't do this is that, from an empirical point of view, we don't really have examples where model-based RL wins over model-free RL, right? And so if I want to show you state-of-art stuff, unfortunately with the models, that is hard to do at this stage of research. Okay. So I just want to quickly mention that we can actually learn options. And so there's this approach called Actor-critic, which I won't have time to describe in detail, but just to give you a flavor of it, it's built on top of Actor-critic. Okay, so the idea is we can parameterize internal policies and termination conditions and take gradients of these a la policy gradient. And then we end up with a set of options that can be used. So we can learn this representation from data. And it can work pretty well in Atari games as well. Now, the other thing that I want to mention, however, is this issue of predictive knowledge. Okay, and so how do we make predictive knowledge for RL agents? Well, one way to think about it is that we want to build value functions. But value functions are tied to rewards, right? Now, what if we think of the reward as just the interesting signal that we want to predict? Okay, it's one of the signals that we might want to predict. And we can think also of the discount factor here as the time scale over which we want to make predictions. Okay, so all I've written here is the definition of VPI. I've just reordered things a little bit so that it's clear that we have a product here of discount factors. Now, the way that I've talked to you about the discount factor so far is as a constant. Okay, but what if we actually make this discount factor depend on state, right? Then maybe we can do more interesting things. All right. And so this is one example. This is actually an option model that's defined in this way as a generalized value function. Okay, and it's in this particular case, it's looking at rewards, but it's also looking at the termination, and this termination actually depends on the state. And so you can think of this termination function, continuation function, but essentially now you'll have a bridge that tells you models can be thought of as general value functions. Okay. Now this is a particular kind of model, which is an expectation model. Okay, it's not a full generative model, but the reason we're using the expectation model is that now, because it looks just like a value function, we can bring to bear all of the machinery that we've built for estimating value functions. Now, what can this be good for? Well, this is a very recent work that we published last NeurIPS, led by Andre Barreto at DeepMind, which is to use these kinds of models to synthesize new behaviors for reinforcement learning agents. Okay, so for example, in this case, we might have an agent that is interested in playing piano. Okay, and so you can think of the usual rewards as learning to play each key independently. But at any given point in time, maybe the agent wants to play a chord, right? And maybe this chord should have a few keys, and maybe some keys should be stronger than others, right? And so one way to think about this is that we can define some cumulants ahead of time that the agent learns to optimize, and then we can combine these cumulants in some way to give us more interesting behavior. Okay, and the general value functions allow us to learn about all these cumulants and keep that knowledge. And so this is just one illustration of this kind of approach for an agent that is inside an arena, and it learns to travel in 3 different directions here. So the red, green, and blue are just 3 directions that the agent has learned. Okay, but now we can actually combine these with different weights and immediately get some way of traveling to many other points. So this yellow cloud here is all of the points that the agent can travel to if it's learned these 3 behaviors. And interestingly, we can even, let's say, tell the agent, don't travel into a certain direction, and even that can be helpful. So I'm going to stop there. I just wanted to leave you with a few concluding thoughts, okay? First of all, I just want to emphasize that RL is quite exciting. It's at this stage where we have built a lot of successful algorithms, and we have built some really interesting theoretical results. And there is lots of things to do. So if people are interested, it's a good time actually to step into the field. There's a lot of open issues, okay? There's still a huge gap between theory and practice. I hope you've got this, this sort of gist when I'm showing you these algorithms that are, theoretically unstable, but in practice they work very well. We somehow need to fill this gap. There may be much better ways to do the function approximation. The approaches that I've showed you all take this attitude of, there's something that people in supervised learning have developed. Let's take it and put it in reinforcement learning and use our own objective function on it. But reinforcement learning has these very peculiar non-stationary targets and has dependencies in the input space. And maybe we should be thinking of developing our own function approximators. And improving, generally speaking, the stability of deep RL algorithms would be really important. And exploration, of course, is a big important problem. So there's lots of things to work on. I will stop there. And if there are any other questions, I'm happy to take them.
Okay, thank you, Doina, for the great lecture. So attendees, if you have a question, now is the time to ask. So I think before that, Sebastian said he had a question for you.
Oh, thank you. Yeah, thanks, Doina, for the nice talk. So I wanted to ask, you mentioned that if you had a model that maybe worked like for some time horizon, that it could be useful for reinforcement learning. And I was wondering, like, if in the context of robotics, let's say you have a model that it's approximate only, and you can use like some horizon, how would you use this for making like the reinforcement learning algorithms more data efficient?
So there's different ways that a model can be used, okay? The one that we've been mostly talking about is almost like driving exploration, right? So it's one particular approach is that we discussed in previous lectures, model predictive control. If I have a model, it's an approximate model. I can imagine doing some steps, and this could be, you can think of that as some form of search. And then we arrive at some particular other state, and we can consider if the choice of action we're currently pegged on based on the current value function is still a good idea, right? Given these simulated steps. So model predictive control is an example of that. Using Monte Carlo tree search, right, with RL algorithms is another example of this, right? So just using a model in Monte Carlo tree search to get to some state and then deciding what to do based on the values of these estimated states. So that can improve sample efficiency just because maybe we're doing now the action choices better. The other aspect of this is to give you the value function updates faster, right? So I mentioned this algorithm called Doina, which does updates to the value function based on the model. So if the model has good knowledge, then you put that into the value function right away without having to get a lot more data, right? And get that knowledge from extra samples. Now, it has to be that the model has been learned and has been learned sufficiently well. So I think part of the problem of what we're seeing in modern model-based RL is that we have models that are kind of approximate, and then if you use the model over and over again too much, right, those approximation errors compound. And so when you're using it in these value backups, that can be detrimental to the value function.
Thanks.
Okay, so if we don't have a question from the attendee, I think this concludes our lectures on reinforcement learning from Doina. Thank you, Doina, for the wonderful lectures.
Thank you very much. It was a great pleasure, and good luck with the rest of the school.
Thank you very much, Doina, on behalf of the whole team. Thank you very much for your talks and the roundtables. It was really amazing to have you virtually here with us in Tübingen. And we hope to see you maybe at some point in the future physically also.
I hope to come to Tübingen and visit in person sometime as well.
The same for us, the same for us. Thank you very much.
Take care. Bye-bye.
Bye-bye.
Thank you.
Bye-bye.